Can you see my screen?
Yes, ma'am.
Okay. In last week, we have started with the design of beams, in which we have discussed about all the steps for design of beams, and then we discussed about the design for shear also, which is the integral part of design of beams steps. We have solved some examples based on design of shear reinforcement, and then we moved back to the design of beams, and we also completed one numerical example based on design of singly reinforced beams. Today, I'm going to start with the design of doubly reinforced beams directly with a numerical example. So just note down this problem statement. We will solve one problem directly because the steps for design of beams will remain same. Only how to find out or how to identify whether the given beam we need to design as singly reinforced or doubly reinforced, that depends upon the mu value. We compare the mu value, that is the bending moment acting on a beam, with the MUR max, that is the maximum moment of resistance shown by the beam, and based on that comparison we decide whether the beam is to be designed as singly reinforced or doubly reinforced. So all of you note down this problem statement first, and then we will discuss about some of the points which are related with design of doubly reinforced beams. So I'm simply reading the problem statement here. A simply supported beam of effective span 5 meter is subjected to ultimate UDL of 40 kN per meter, inclusive of its self weight. Design the beam if the overall depth is restricted to 400 mm and width of supporting column is 230 mm. M20 grade concrete and Fe415 grade steel are used. So in the given data, if you see the effective span of the beam is given, the total load acting on a beam in the form of UDL is also given, which includes the self weight of the beam also. So we don't need to calculate the self weight of the beam separately. Then another condition is given in the problem, that the overall depth of the beam is restricted to 400 mm. So when we start the design of beam steps, we first decide the dimension of the beam, in which we also decide the depth of the beam. Now that is not required here because the overall depth is restricted to 400. It means we cannot use the overall depth value more than 400 mm. So we have to adopt the same value as the 400 mm overall depth. And normally when such restrictions are given to the depth, normally we need to design such beams as a doubly reinforced beam. Obviously we have to check the comparison between MUR max and MU. We have to check these values and then we decide. But if the depth is restricted, we normally go for doubly reinforced section, because the total moment which is acting on a beam can get resisted better when we go on increasing the depth. Okay, so if we increase the depth of the beam, the moment of resistance of the beam also increases. But here there is a restriction for the depth. So obviously we have to increase now the area of the steel to resist the overall moment acting on a beam. And for that we have to go for the doubly reinforced beam. Okay, so have you noted down the problem statement? Students?
Yes, ma'am.
Okay, everybody has written now?
Yes, ma'am.
Okay. Now, before going to the solution, let me recall the concept of doubly reinforced section. If you remember, this is the diagram which I have used to explain you the concept of doubly reinforced section. So when we wanted to find out the moment of resistance given by the doubly reinforced section, the entire section we considered divided into two sections, section 1 and section 2, in which in section 1 we consider that the steel is provided only in the tension zone, that is in the bottom area of the column, of the beam. And second section is the combination of both the steel, that is the steel provided in tension zone as well as steel provided in compression zone, just for sake of simplicity in the calculation. Okay, now when we design any beam as a doubly reinforced section, we don't know actually what is the area of the steel provided in first section and what is the area of the steel in second section. That we have to decide. Okay, area of the steel we decide. when we design the beam. Dimension of the beam also we design when we decide when we design the doubly reinforcing section. So initially we have only the total moment acting on a beam. We don't know what are the dimensions, we don't know what is the area of the steel, and hence total AST we cannot divide as section 1 and section 2. And hence when we start with the design, we have to deal one section as a balanced section. So section 1 we consider as a balance section. Whatever the amount of steel required for balance section we provide for the section 1, and accordingly we calculate the mu1. So total moment of resistance shown by doubly reinforced section, if it is MUR, we divide it into two values, MU1 and MU2. That is a moment of resistance shown by section 1 and moment of resistance shown by section 2. So total moment we divide for sake of simplicity as MU1 shown by the balance section, and the remaining moment will be considered as shown by the or resisted by the section 2. So the formula, the total formula of MUR, which we calculate as MU1 plus MU2, we calculate like this. Now MU1 is calculated as CU1 into ZU1 or TU1 into ZU1. That is the total force of compression into lever arm or total force of tension into lever arm. So here to calculate MU1, or rather we have the MU1 value, so that is considered as a MUR max, and we use this formula for MUR max, that is either 0.36 FCKB into XU into bracket B minus 0.42 XU max. That formula, that is CU into ZU, that formula we use, or we can use TU into ZU. Now, when we use the second, that is TU into ZU, we don't know what is AST1. So obviously we have to make use of the first formula only to find out MU1. Okay, but initially, as we know, the total moment of resistance MUR, we simply divide it as MU1 plus MU2 depending upon or by comparing it with the total bending moment acting on the beam. See, I'm not going to increase your confusion. Once we start solving the design problem, it becomes clear to you how we are doing the further calculation. But just keep in mind that section 1 is treated as a balanced section when we design the doubly reinforced section. Once we have the value of MU1 and MU2, we can easily find out the AST1, that is the area of the steel provided in the tension zone for section 1 and section 2. Okay, so these are the formulas of AST1 and AST2, which we have to use further for calculation in the design. Once we find out the total tension steel, we have to find out the total area of the steel provided in compression zone also, that is ASC. Okay, that is calculated by using this formula mu2 divided by FSC into bracket D minus DC. So if you don't have the notes, earlier notes, when we consider the problems based on analysis of doubly reinforced section, right now if you don't have those formulas, you just take a pic of this particular slide to find out AST1, AST2 and ASC. We need to use these formulas. Okay, just tell me once you finish taking picture of this slide. Is it over? Have you taken a photograph? Or you can note down these formulas in your notebook. Students, are you there?
Yes, ma'am.
Have you noted down these formulas?
Yes, ma'am.
Okay. Also note down these formulas, MU1, MU2. You need to write down these also, because we will require these formulas. Is it over? Students? Are you there in the class? Hello?
Done, ma'am.
Okay. Now let us start the solution. Let me write down first the given data. tell me the given data.
Effective span 5 meter.
Yes, so L effective is 5 meter. Then
WU 40 kilonewton per meter.
WU is 40 kilonewton per meter. This is the ultimate load, right? So we don't need to apply any factor of safety to find out the factor load. It is the factor load itself. Next,
D is 400.
this is the overall depth, right? So overall depth, that is total D, capital D is given as 400 mm. Then the grade of the steel and grade of concrete is also given. So let me know what is the grade of the concrete.
20 Newton per mm square.
So FCK is 20 Newton per mm square and
FY
FY
415.
415 Newton per mm square. Okay.
Width of supporting column 230 mm.
Okay. So I will just write down width of column as 230, right? 230 mm. Okay. So this is the given data. Now let us start with the first step. We have to consider the first step in the design, that is deciding the dimensions. First dimension, that is the depth. Depth is already given. We have to decide the width. So what is the width of the beam? So first of all, we have to calculate size of beam. So I will simply write down here size of beam. Yes, width.
Width of support.
Okay. So we will adopt the width of the beam. Width of beam is equal to the column width, that is 230 mm. Okay. Overall depth D is already given, so we have to adopt that only. So D is 400 mm. So we have to provide the cover now. So let us provide or providing effective cover as 50 mm. Okay, we have assumed that the cover is 50 mm. So what is the effective depth now? Effective depth of the beam D will be 400 minus 50. So we are getting 350 mm as the effective depth of the beam. Okay. Now what is the second step?
Calculation of ultimate bending moment and shear force.
Yes, so load is already given. So we will calculate the ultimate bending moment and shear force. So as the given beam is simply supported, so the maximum bending moment formula is WL square by 8. So this is WU L effective square by 8. I have to write down. What is the value of WU? It is 40 kilonewton. So 40 into effective length is already given as 5. So we don't need to calculate now the effective length as we did for earlier problem or design of singly reinforced beam. So tell me now, what is the MU value? This is nothing but your MU value.
125
125.
125 unit.
kilonewton meter.
Okay. Now similarly calculate the shear force. So shear force formula will be WU into L effective by 2, WL by 2. So 40 into 5 divided by 2 VU value. Tell me the value.
100.
100. Always tell me the unit also. Huh? Don't forget to write down unit. It is important. Now, we know the bending moment, we know the shear force. Now, the next step in the design for doubly reinforced section, that we have to check the moment value. So the third step I will write down here as finding the moment capacity. Okay. So for finding the moment capacity, now I have to calculate MUR max. So what is the formula for MUR max?
0.36 FCK V into XU max
Hmm.
into D minus 0.42 XU max.
Yes, D minus 0.42 XU max. What is XU max value? Tell me. It depends upon your grade of the steel, right? So what is the XU max value? Look into the steel, IS code, IS 456, and tell me the XU max value.
Ma'am, XU max is 0.48 D.
0.48 D. So tell me the value now here. D is 350. So XU max is
168.
168.
168. Okay. Now put these values here in MUR max formula and tell me what is the MUR max you're getting. FCK is 20, B is 230, XU max is 168, D is 350. Put all the values and tell me MUR max value. Yes, what is the value you're getting? Students, I'm waiting for the answer.
77.74.
Yes. 77.74 kilonewton meter is the MUR max. Okay. Now, what is the total moment acting? Total MU is 125 kilonewton meter. Okay. So, this value MU is less than, MUR max is less than MU. Okay. MU is 125 kilonewton meter. So, MUR max is less than MU. What does it indicate? What is the meaning of this statement?
Design as doubly reinforced.
Yes. So design the beam as doubly reinforced beam. Okay. So if you consider again the MUR max value and MU value, here our MUR max value is less than MU value. So total MU is to be resisted by two parts, that is MU1 plus MU2. And we have already MUR max value, which we have to consider as MU1 here. As I discussed earlier, that in case of doubly reinforced section, when we consider the same section divided into two sections, section 1 and section 2, the first section we deal it as a balance section. So here we have already calculated MUR max value. This value we will consider as MU1. Okay, so just write down a statement. MU1, MU is equal to, or you just write down, for doubly reinforced beam, for doubly reinforced beam, mu is equal to mu1 plus mu2. Okay, so taking mu1 is equal to mur max equal to, what is the value mur max? 77.74 kilonewton meter. So my mu1 value is known to me. Mu2 value, by making use of this formula, I know mu, I know mu1, I can find out mu2. So mu2 is equal to mu minus mu1. So this is 125 minus 77.74. So what is mu2, you're getting?
47.26.
mu2 is equal to 47.26 kilonewton meter. Okay, so I know now mu1 value, I know mu2 value. I can find out now AST. You have already the formulas for AST1 and AST2. Okay, so we can simply find out AST1 by making use of the formula. I will go back to the slides which I have shown, and I have shown the formulas also. So AST1 formula is this and AST2 is this. So let us make use of these formulas to find out AST1. Okay, so just write down next step as calculation of, what is that, step number 4. Calculation of AST. Step number 4, calculation of AST. So what is the formula? AST1 is equal to mu1 divided by 0.87 Fy into bracket D minus 0.42 XU max. Am I right? Let me check the formula again. Yes. So put all the values here now in this equation. So what is mu1? mu1 is 77.74. So 77.74 into 10 raised to 6, because I am writing Fy in Newton per mm square, divided by 0.87 into 415 into bracket D is 350 minus 0.42 into, what is the value of XU max? 168.
770.53.
Wait, huh? So 770.53
53.
mm square. This is the value of AST1 I'm getting. Okay. Now let us find out AST2 also. So AST2 is equal to, same formula, instead of mu1 we have to put mu2. So it is 0.87 Fy into bracket D minus, this is DC. Am I right? I will go back to the slides to check the formula of AST2. So it is mu2 upon 0.87 Fy D minus DC. DC is nothing but your effective cover. So let us put all the values. What is the mu2 value? Tell me.
47.26.
Yes. So 47.26 into 10 raised to 6 divided by 0.87 into 415 into bracket D is 350 minus DC is 50. So AST2
436.32.
436.32. This is your AST2. So let us find out now total area of steel, AST, which will be AST is equal to AST1 plus AST2. Tell me the addition.
1206.85.
1206.85 mm square. Okay, this is the required area of the steel in tension zone. We have to check this value against the minimum and maximum area of the steel as per the criteria given in code. Okay, so AST should be greater than AST minimum. So what is the formula for AST minimum?
0.85 BD upon FY.
0.85 BD upon Fy. So calculate this value. It is 0.85 into B is 230 into D is 350 divided by Fy is 415.
164.87.
164.87, and our AST required is greater than AST minimum, so that's fine. Suppose your AST calculated is not coming greater than AST minimum. In that case, you have to provide the minimum area of the steel. Okay. So we have to check it against the maximum value also. So AST max, how it is calculated?
0.04 into B into capital T.
Yes. So find out this value. B is 230, capital D is 400.
3680.
Okay. So our required AST value is well within the two limits. Minimum, it is greater than minimum value and it is less than maximum value. So for this AST, we have to calculate now number of bars. So let us assume now the diameter of the bar as 20 mm. So let us consider 20 mm diameter bars. So we have to find out now the number of bars. So number of bars will be equal to AST, or I will directly write down the value. What is the AST? 1206.85. 1206.85 divided by area of the single bar, so which is pi by 4 into d square. Tell me the value.
3.84.
3.84, that means 4, right? Number of bars we need to provide are 4. Okay, so just write down one statement below here, or you need to first calculate the percentage of steel provided or AST provided. So let us calculate AST provided first. AST provided is equal to pi by 4 into d square and such 4 number of bars. So what is the value?
1256.64.
Yes. Okay. So for this, just calculate the percentage of steel also, because that value we require further in the design of shear reinforcement. So let us calculate percentage steel as AST provided divided by B into D into 100.
1.56.
1.56% is the AST provided. All right, fine. Now, the next important point that we have to selected now the bar diameter and we calculated number of bars required. The next point is we have to check the width for beam. Okay. So last time while considering this check for width, what we did, we simply equated the total width of the beam to the formula, and in that formula we kept C2 as unknown. C2 is nothing but the spacing between the bars. Now here, the another method is that C2 we can calculate earlier by considering the criteria given in code. That is, out of the three values, we have to adopt the greatest one. That is, what are the three criteria? One is the maximum diameter of the bar. Second is the largest diameter of the bar if we are using combination of the different diameters of the bar. See here, we have provided total four number of bars having same diameter 20 mm. Sometimes practically to achieve economy, the combination of two different bar diameters is also done. That is, instead of providing all four bars of 20 mm, I can go for say 20 mm two bars and say 16 mm two bars. Okay, because if you compare the value of the required AST is 1206.85, whereas provided is 1256.64. So we have already provided almost 50 mm square more area. Okay, so that we can adjust by reducing the bar diameter. We can provide the close area, whatever is required, that is 1206 is required. So we can provide say 1210 by adjusting the bar diameter. So in this fashion, we can consider economy in the design. Okay, right now, for sake of simplicity, even in the examination also to avoid these calculations, you can directly provide, you can show the calculation like whatever right now we are showing. Okay, but practically when we consider or when we do the design of the beam, we have to take care of the economy also, and that is done in this fashion, that we consider the combination of different bar diameters. Now here we need to consider the combination whether 220 and 216 mm will be sufficient, or we have to go for 220 and 212, or we have to go for 320 and 112, or 320 116. That combinations we have to check, and then accordingly the suitable combination we have to adopt. Okay, in examination, to reduce the time of calculation, you can show the calculation like right now whatever we are showing. Is it clear to everybody? Now, for that, we will adopt now the next check for width, in which we have a formula. Tell me the formula.
2C1 plus N phi
Hmm.
plus N minus 1 C2 should be less than B.
Okay, this should be less than B. Okay, now I will adopt C1 and C2 value. N we have already calculated. N is nothing but number of bars. Bar diameter is already known to us. So let C1 be 30 mm. C1 is nothing but the side cover to the beam. So I will simply write down it in the bracket side cover. And C2 is the spacing between the two bars that has a criteria that it should be the greater of first criteria, the bar diameter, right? So what is the bar diameter? 20 mm we have adopted. Second criteria, the bar diameter of the greatest size. All four bars we have adopted of same diameter. So this value will remain again same, 20 mm. And third one, the criteria is maximum size of aggregate plus 5 mm. Okay. So normally maximum size of aggregate we adopt is 20 mm. So this will be 20 plus 5 equal to 25 mm. So out of these three values, we have to adopt the greater one. So C2 is 25. We are adopting. Okay. So let us put all these values in this equation. 2C1. So this is 2 into C1 is 30 plus N phi. N is 4. Phi is 20. Okay. N phi plus N minus 1 into C2. It is 25. Okay. What is this value? Tell me.
215.
215.
215 mm. And what is our B value? It is 230 mm. So this value is coming less than B. So Okay, our check is correct. Okay, or whatever the values or spacings we have adapted, spacing between the two bars, the side cover, everything is perfectly all right. Okay, because we are getting this check. Suppose if we are getting instead of 215 mm, suppose we have obtained it as 240 mm, suppose. Okay, our width is 230 mm. So 240 mm, if that width is coming, it means either we have to reduce the bar diameter without compromising the area of the steel requirement, or we have to increase the dimension. These are the two possible ways to have this check. Okay, so once you finish the all the calculation, that is deciding the size of the beam, the calculation of area of the steel, we have to go for this check. Okay, don't forget to show this check. Right now our check is coming satisfactory. So we have completed the calculation for steel in tension zone. We are designing it as a doubly reinforced. Okay. So the next part is that we have to calculate the area of the steel in compression zone. Okay. So I will write down it as calculation of AC. Calculation of AC. Okay. AC is nothing but area of the steel in compression zone. If I will go back to the slides and if I want to show you the formula of ASC, what is the formula? It is mu2 upon FSC into bracket D minus DC. Now we already have the value of mu2. We know what is D value, what is DC. We don't know FSC. What is FSC now? What is FSC? What is the meaning of FSC?
Stress in steel in the compression zone.
Yes, FSC value. Fy value is given to us. Fy is nothing but the stress in steel, which is in tension zone. We don't know what is the stress in steel in compression zone right now, and we need to calculate that value. Okay, how to find out now FSC? Students,
87 FY.
no. Why 0.87 Fy? Why 0.87 Fy? Okay, you forgot the calculation. As we proceed further, the earlier calculations you forgot. Okay, if you remember, we have solved the problems based on analysis of doubly reinforced section, in which if we are using mild steel, that is when Fe250 grade steel is used, FSC formula is a straightforward formula, that is by making use of Hooke's law and the epsilon SC value, we can directly calculate FSC. Okay, we have all the relation, we have to use all the relation related with stress and strain curve. Okay, now when we go for Fe415 grade steel, the calculation for FSC is not so straightforward because the stress strain curve is not linear, and we have to make use of the table, the larger table which we have prepared. Okay, I will go back to the slides now. I have included this table in the slides just to recall the concept. Do you remember this table? You only
Yes,
form this
ma'am.
table. So we have to make use of this table to find out FSC value. Now, to find out FSC value, first of all, we have to calculate what is the strain in steel. Okay, that is epsilon SC. So let us calculate first epsilon SC value, and then we will go to this table again to calculate FSC. Okay, so let us find out epsilon SC value. Tell me the formula.
0.0035 1 minus DC upon XU.
Yes, this is the formula. XU, we have to make use of XU max here, huh? Again. So I will erase this and write down again D upon XU max. Because the first section we have considered as the balance section. Okay, so this is XU max. Put all the values. in the equation and tell me epsilon SC. So 0.0035 into bracket 1 minus 50 upon. What was the XV max value?
168.
168. Okay. So tell me epsilon SC.
2.46 into 10 raised to power minus 3.
Tell me the decimal point. Point not
246.
24
246.
246. Okay. So for this epsilon SC value, now we have to find out FSC. So I will go back to the table. See, in the examination, you should be able to prepare this table at the time of exam period, because this table is not available in code as code. Don't waste your time in searching this table. In this table, you have to prepare in during your examination period quickly, and then make use of the values to find out the FSC. Okay. Now our value, total strain value, that is epsilon SC, we have calculated as point not 246. So that value is in between. Okay, I will go here. That value is in between these two values. Okay, 0.00241 and 0.00275. So we have to interpolate the value between these two to find out the corresponding stress value. Okay, so I will simply write down here 0.00241 and 2 epsilon SC value and FSC value. So this is 0.00241 and 0.00246 and 0.00275 na, or 76, 75. Okay, so corresponding to this, let me check the FSC value, 342.83. so this is 342.83, and this value also,
351.85.
yes, it is 351.85, right? We have
Yes,
to
ma'am.
find out this value, FSC. So quickly do the interpolation and tell me what is the FSC value you are getting.
Uh, 344.156.
344.15.
156.
Let us consider 16. 16 Newton per mm square. So this is the value of FSC. Now let us make use of the ASC formula to find out area of the compression steel. So it is mu2, I will write down the formula again, divided by FSC into bracket D minus DC. So mu2 value was, tell me the mu2 value, 46 point something was that, na? mu2 value
47.26.
47.26 into 10 raised to 6 divided by FSC is 344.16 into bracket D is 350 minus DC is 50. Okay, put all the values and tell me ASC, or do the calculation and tell me ASC.
457.73.
467.7.
7.3. Okay, no problem. Now we have calculated the total area. In the code, it is not specified that for compression steel, we need to check what is the area of the steel within the range, that is AST minimum, AST maximum. Whatever we have calculated calculated, that is not suggested for compression steel. So we don't need to show that calculation here, that what is the minimum area of the steel and what is the maximum, and whether the ASC required calculated is does fits and in that range. That calculation is not required. So directly now we will find out the number of bars. So again, I will here assume here that I'm considering 20 bar diameter. Okay, so I'll write down, let us consider 20 diameter bars. So number of bars will be AC 457.73 divided by area of the single bar. What is the value? What is the value?
1.46.
Again?
1.46.
1.46. It means 2 bars. Okay? 1.46, such odd number of bars we never provide. So just write down one sentence. Providing 220 diameter bars adds compression reinforcement as compression reinforcement. Okay, here your area of the steel calculation finishes. Now the next step is last step. What is that?
Design for shear reinforcement.
Correct. So design for shear reinforcement. This you have to do as a homework. Okay, design for shear reinforcement. Okay, at the end, I will simply draw the diagram here also. Once you complete the design for shear reinforcement, you have to show the diagram of the beam. So I will simply show you the diagram, how it is expected. So this is my beam cross section. I provided 420 bars in the bottom and 2 in the top. Okay, so these are 20 4 bars and 2 bars in the compression zone. Okay, so this is my neutral axis. Total width we have provided is 230 Total depth is 400 and the effective depth is 350 with effective cover of 50 and this is 20 bar diameter. Now along with this you need to provide the shear reinforcement also, right? So after design you will tell me what is the shear reinforcement you are getting. I am simply drawing it by a diagram here. I'm showing here a diagram. So this is my shear reinforcement, which will go like this. Okay, normally we go for 2 leg shear force, and here at one end it will get bent like this. and we have to provide the details of these also. Okay, so after the design, whatever the diameter of the shear reinforcement or stirrups you have adopted, that diameter and its spacing you have to mention here. It is clear from the diagram that I have provided two-legged stirrups. So two-legged, say 10 mm diameter at spacing, whatever you have adopted, center to center, that you have to show here. Is it clear? So this is the diagram. This diagram is expected once you finish the design of beam. Is it clear, everybody? Design of doubly reinforced section. The calculation part is little more because we have to calculate MU1, MU2, then AST1, AST2, ASC also. So that calculation part increases in case of doubly reinforced section. Any doubts in this design of doubly reinforced section? Students? Hello?
No, ma'am, no doubt.
Okay. So just for practice, I have included one more problem statement. All of you quickly note down this problem statement. And you solve this as homework for practice. Okay, only the change in the problem statement is that the load is increased. Whatever the problem we have solved right now, in that we have used 40 kilonewton per meter load. Now it is increased to 50 kilonewton per meter. So for that increased value, we have to design the beam. Is it over? Students?
Yes, ma'am.
So let me give you now the link for attendance. Just give me 2 minutes. I will paste the link here. I forgot to copy that link today in the slides. I hope everybody has given the attendance in your chat box also. I'm checking both the attendance regularly. Whatever the attendance you give through the link which I provide and also in the chat box, both I am considering and taking its reference. I have provided the link here. So give your attendance through this link also quickly. Have you got the link, everybody? Students?
Yes, ma'am.
Any doubts up till now in the design of beam? In the next lecture, we will, yes.
Ma'am, now in the for the design of shear reinforcement, do we still consider the zones separately for the spacing?
You can consider. It's up to the designer. If you want to achieve economy, you can consider the zones separately, or you can consider the design for only the maximum shear force. Okay, see if what is my suggestion, see for all of you, in the examination, if it is clearly mentioned that do the curtailment of reinforcement, then only you consider the zoning and then solve the problem. Otherwise, you simply consider the maximum shear as the total shear acting on a beam. And for that maximum shear, whatever the design you are getting for shear reinforcement, provide that throughout the beam. In the examination, what is checked? Whether the steps, what is the concept of the shear design, whether you have understood well or not, that is checked. And accordingly, the marks will be given. Because every student's design will be different, their assumptions will be different. So we never consider what is your final answer. We always consider the steps, whatever you are considering for the design, whether the steps are well understood by you or not. So in the examination, you can consider only for the maximum force acting on the beam, and for that you can complete the design of shear reinforcement. But if in the problem statement if it is clearly mentioned that show the curtailment or do the curtailment of shear reinforcement, in that case you have to consider the zones in the beam, and accordingly you need to design the shear reinforcement. Is it clear?
Yes, ma'am. Ma'am, and in the problem we solved in the last lecture, for the design of shear reinforcement, VU was 78.45 kilonewton, and VUC max based on the grade of concrete, it was coming as 289.8, which is greater.
Okay.
So we'll have to design the whole beam again.
No. That correction I forgot to explain you last time. Good, Akshata. You brought this to my notice again. Let me go to the steps, whatever we have discussed for the shear reinforcement. I will show the steps again. And there is one correction. Last time also we discussed, and I forgot to explain you that correction. So let me present this first. Okay, these steps, right? Here there is a correction. VUC max should be greater than VU. I think last time whenever I have explained you, I have shown these steps now. This value was less than VU. Am I right?
Yes, ma'am.
So that was the correction. By mistake, it was less than VU. It should be greater than VU. And if this value is not coming greater than VU, in that case, you need to resize the section, or you need to change the grade of the concrete. Change the grade means you have to go for, or you have to adopt the higher grade of the concrete. Is it clear?
Okay, ma'am.
So there is no need to resize for the earlier problem. VUC max should be greater than VU. Everybody, please make this correction in your design steps for shear reinforcement. Is it clear? Any other doubt?
No, ma'am.
Okay, so shall I stop now the presentation?
Ma'am, can you upload the previous lecture video?
Yes. I could not upload due to some other official works. So today, definitely I'm going to upload all the earlier lecture notes and videos also, including today's lecture notes and video. Okay, so by today evening, you will get all the notes on VOLP.
मॅडम
हा
ते तुम्ही व्हाईट बोर्डवर जे वर्क करता ना ते पण भेटेल का?
त्याचा PDF करून पिक्चर फॉर्मॅट मध्ये मिळू शकतं. पण आता आजचं जे लेक्चर आहे, जे आता अजूनही व्हाईट बोर्ड वरती आहे, ते मी सेव्ह करते ऍज अ पिक्चर आणि पाठवेन तुम्हाला. अदरवाईज आय एम शेअरिंग द व्हिडिओ ऑल्सो. तुम्ही व्हिडिओ आपलं जे लेक्चर चालू आहे त्याचे व्हिडिओ आहे, ते व्हिडिओ मी VOLP वरती अपलोड करतेय. ते व्हिडिओ बघितला तर तुम्हाला सगळं मिळून जाईल त्याच्यामध्ये. ओके
ओके.
All right, so shall we start?